So range. So we said that the range is the easiest to understand. Anybody will understand when you tell them that minimum is 5 and maximum is 1500. But the problem was that, first of all, it is unbounded, so it's not very useful, because if you would have taken more observations, it would have been even bigger range and bigger range. So it's unbounded. And then generally the range only indicates the outliers. It doesn't say that, okay, well, there was one guy who was at 5 and one at 15,000, but everybody was at 10. Right? So it doesn't really give any indication of that. So it's only outliers information. And therefore, only the time you will use it when the variable is bounded. When you know that it cannot be anything less than 5 and it cannot be ever be more than 1500, and that is an important piece of information for whatever reason, then you say that this is the number. Okay? Otherwise, the other ones are better. And one of them is variance. And by the way, sample variance. Now here is one more thing. Let me explain. That there are two variances. Population. We talked about this, population versus sample, right? The word sample came from French. Example, but and this is in the book. If you read the book, the thing is that the statistics. When we talk about the population, we use the Greek letters. Mu, sigma, alpha. When we talk about the sample, we use English letters, S, and so on and so forth. So sample variance is S square. All right? Because this is the measured as compared to the, if you are writing a distribution, then you will write sigma square. All right? So S square is, you take ith value minus x bar, where x bar is the mean, squared, and add up all of them and divide by n minus 1. Right? All right. So notice that the divisor is n minus 1 and not n. For the mean, the divisor is n. And the reason is that if I gave you n minus 1 of these differences, these terms that you're adding n terms. But if I gave you just n minus 1 of them, you would know the last one. How? Because the differences will add up to 0. So you can add up. And why they will add up to 0? Because by definition, x bar is the sum of them. So if you bring x bar on this time, you will get a 0 on the other side. Right? So only n minus 1 of them are independent. The nth number you can always guess from the n minus 1 numbers. And therefore we call it degrees of freedom. In calculating S squared, you have only n minus 1 degrees of freedom. All right? And so you divide by n minus 1. Now, let me tell you, if instead of x bar, but somehow we knew mu. Mu, what is mu? Mu is the population mean. Right? If we knew population mean by some method, and we didn't have to estimate it from the same sample, and we put a mu there, right? Then what will happen is, in that formula, you will have n degrees of freedom. Because given n minus 1, you won't be able to compute the last one. Do you get that why? Because if I knew mu, then the observations don't have to add up to mu. They will not add up to, basically mu, right? I mean, the average of those observations will not be mu. It will be something different. And therefore, given n minus 1 observations and given mu, you cannot compute the last one. When you compute the sample mean from the observations, then given n minus 1, you can compute the last one. If suppose somebody gave you the sample mean and n minus 1 observations, you can compute the last one. Right? But if somebody gave you n minus 1 observations and the population mean, then you cannot compute the last observation. It's still independent. So if this is mu, then you divide by n. If it is x bar, you divide by n minus 1. So another way to understand this is that in any formula, and there will be lots of different formulas coming up in the rest of this course, you see how many variables you have already estimated from the same sample. So you were given n observations, but in this formula you're using x bar, which you have already estimated from the same sample. So you lost 1 degree of freedom. Okay? So if there was another formula where we compute something else in which we use x bar and s squared somehow, that quantity will have how many degrees of freedom? How many degrees of freedom it will have? If you have already used, if in that formula I use, let's say some quantity, let me call it kq, and in that I use on the right side x bar and s squared along with the n observations. How many degrees of freedom will that have? N minus 2. This I wanted to get the formula. Basically, you have used up 2 degrees of freedom. Why you have used up 2 degrees of freedom? Because you are using s square and x bar, which you have calculated from the same sample. Actually, it would have helped if I had written something here. I didn't write it because I don't have a real formula, but there will be formula coming up. So let's say we say k, you are computing, which is some function of x1, x2 to xn, and then x bar and s squared. Okay? So you are given n observations, but x bar has been computed from the same observation, and s squared has been computed from the same observations. So you lost 2 degrees of freedom, and therefore k will have n minus 2 degrees of freedom. If you just compute everything from this, then there is n degrees of freedom. If you use something which has been estimated from the same thing, then you lost 1 degree of freedom, so you have n minus 1, and so on. The more things you estimate from the same sample and use it, you lose degrees of freedom. Yeah.
Why do we need to use the degrees of freedom number? I mean, why is it important to?
Oh, this is important because anytime you estimate any quantity, you have to divide by the degrees of freedom. So here there are 2 formulas right here. Here you divide by n minus 1, here you divide by n. But there will be other formulas coming up. There will be lots of formulas coming up in the course. In every formula, you have to divide by the right degrees of freedom. Yeah.
So, if you replaced x bar with mu in this equation,
Yeah.
and you had your sample size was equal to the population size.
Well, if it was equal to the population size, then basically you sample the whole population. It's not a sample; it's the population. The sample size will never be equal to population size. Then it's not a sample anymore.
Yeah, okay. So then the concept of degrees of freedom doesn't even extend to that.
Well, it extends to that degree, but once you have the whole population, then you're not estimating anything. You should get everything. There is no probabilistic left. This is all deterministic then. Let's say, we have a class here of 8 people, all right, and actually there are supposed to be 9, so 1 is missing, but let's say 8 people, that's the population, and everybody is here, then I don't have to estimate anything. The thing only sample starts is only when if I take a part of it, and that is why it is called example. The French of example is a sample or something like that, so sample came from there. So if it is a sample, then it is different. Okay, all right. Any other question? Yeah.
Can you repeat that? So you said that if you put mu instead of x bar, you have 0 degree of freedom?
You have n degrees of freedom.
Oh, n, okay. But
Because you have n observations. You still have sample of n observations. You don't have the whole population.
okay.
You still have, you are using mu because mu is known. You are not estimating it from the sample. Mu is known for some reason. All right. So the main thing I wanted to get you from this slide is not so much variance, which you already knew, was degrees of freedom. Okay? And there are several things that we have already talked about. The variance, which we'll repeat again, is that variance is not useful, is not preferable because its unit is, what is wrong with its unit? Square of the something. So that is not easy to interpret. And therefore, better thing is standard deviation, and even better than that is coefficient of variation, which has no units. Standard of deviation has the same unit as the quantity that we are talking about, and coefficient of variation has dimensionless. Dimensionless is always better than dimensions. All right, moving on to percentiles. Percentiles, basically, we will use quite often, and they are used quite often in the real world. So we specify, say, 5 percentile or 95 percentile rather than minimum and maximum. It's better than minimum and maximum because minimum and maximum have no bound. More observations you take, minimum and maximum will go up, but percentiles have, at least they are more stable. They are more stable. So basically, they don't just change if you add more observations. So we express a fraction. So that can be done for any variables, even for a variable without bound or with bound. And when we express as a fraction between 0 and 1, we call it a quantile. So 0.9 quantile is same as 90 percentile. So this was, we explained before, like alpha quantile is same as 100 times alpha percentile. Sometimes people call it fractile. Fraction between 0 and 1. And at 10% they are called this and deciles, and then at 25% they are called quartiles, which is the next slide. So anyway, so percentile is 5% and 95% is, we will use quite a bit. 90 percentile we will use quite a bit. Any question? Yeah?
So is the 5 percentile and 95 better than specifying the minimum and maximum?
Of course. The thing is, everything I am telling you here is a guideline, not a rule. So this I want to emphasize in every class, and you will hear every time. There are situations when somebody needs minimum and maximum, and then you tell them whatever they need. But if you are the analyst, you did the measurement data collection, and you have the choice, then your justification would be that percentiles are more statistically stable because they are bounded. Whereas the minimum and maximum may not be bounded. If they are bounded, obviously, then you can use them at those are good. But if they are not bounded, then percentiles are better indication. And that's why you hear so much percentile. I mean, when they talk about in the real world. Quartiles are same as percentile, except that they happen at 25%. So we talk about first quartile, second quartile, third quartile, and second quartile is also the median. And you can estimate any percentile or quantile by just sorting the observation and taking n minus 1 times alpha plus 1th element in the ordered set, where this square bracket is used to denote rounding to the nearest integer. So this doesn't say rounding up or rounding down, it says rounding. That means if it is 10.5, you go to 11th, if it is 10.4, you go to 10th. And for quantity exactly halfway, if it is exactly 10.5, then you take the, so this is a contradiction right here. This is a contradiction because just a few slides ago we said that you take the average of the two. Now here we are saying that you use the lower integer. There is no strict rule. This is different authors vary on different things. And since we have already said once that we take the average, we just take the average. And I would change this one. All right, everybody understand what the change is? Everybody understand what the change is? That I am not agreeing with the last sentence on the slide, which is, basically, is that for quantity exactly halfway, you might want to just take the between the two rather than taking the average. And rather than taking the lower, take the average. Semi-interquartile range. So just like we have 5 to 95, there is a 25 to 75, and that is called semi-interquartile range. Basically, that is from 25% to 75%. 25% is called Q1, 75% is called Q3. You take the difference between the two, and halfway between them is semi-interquartile range. Now here is the thing, having said all this, I think I'm going to de-emphasize much of this because I have not seen much of this being used. So while, maybe next edition of book this will go away. Next we have mean absolute deviation. So here we don't care how far you are from the mean, whether you are lower or above. We just take the difference from the mean, take the absolute value, and then we do. So this is somewhat similar to standard deviation, not exactly that, because for standard deviation you would have taken the square and then the square root. Here we are just taking the absolute value. Okay, and obviously this is for the case where there is some symmetry from the mean both sides, so the lower is equally bad compared to the higher, and so on and so forth. And so this is another one for completeness. Not that I have seen too much use of this. So comparison of various measures. So range is affected considerably by the outliers. So basically we don't like that because it is not statistically stable. Sample variation is also affected by outliers. All right, but to the effect is less. Mean absolute deviation is next in resistance to outliers. So that is the reason for using that mean absolute deviation, is that outliers have linear effect as opposed to square effect. Well, by the time you take a square root, probably it becomes the same. Semi-interquartile range is very resistant to outliers. So when you take 25% and 75%, that is much more stable than 5 and 95. So you come there. If distribution is highly skewed, outliers are highly likely, and then you prefer one of these, which is SIQR. In general, SIQR is used as an index of dispersion whenever median is used as index of central tendency. And so if you have reason for justifying median, you can justify SIQR. For qualitative, that means categorical data, the dispersion can be specified by giving the number of most frequent categories that comprise the given percentile. So for example, top 90%, that would be one way to specify the dispersion, that the top 90% or 90% of the market consists of PCs and Macs. We don't care for the rest. So that's the 90 percentile. The categorical data. So let's take an example. So this is a set of numbers. We sort it out. Now if we want to get the 10th percentile, we put 0.1 here times 31. 31 is the total number is 32. So we did n minus 1. Remember this one, n minus 1 times alpha plus 1. So we are going to do that. N minus 1 times alpha plus 1. So that comes out 3.1 plus 1 is 4.1. Rounded basically, not up or down. So 4.1 rounded is 4. And therefore you take the fourth element. Here 90 percentile, you take 9, so that is 27.9 plus 1, 28.9. Now rounded would be 28.9, rounded would be 29. So that is that number. First quartile is 0.25, and then rounding will drop that off the fraction. So it would be 7.75 plus 1, 8.75. So you go to ninth element. This is 15.5 plus 1, so 16.5. Now here is the thing, basically it says 16th element following the rule that you take the lower one. But I think I would be consistent and say that from now on we just take the average of the 16th and the 17th. Now here it is not going to make much difference because 16th and 17th. 16th is 4. Is this the 16th? 4.5, and 17th is 16th is 3.9. 3.9. So I don't know. It will not make a difference whether you take the average or do the same thing. But in some cases, if it was big difference, then the question of taking lower or upper will make a difference, and I would safe side. I would take the average. Median is we already talked about median. Then we talk about third quartile is 75. So 31 times 0.75, and then add 1, you get 24th element. So now you know how to do that, and then you know how to do SIQR by Q3 minus Q1 divided by 2, Q3 minus Q1 divided by 2. Any question about this example?
Maybe
Yeah.
a question myself.
Yeah.
Let's say that instead of, on the third quartile, instead of getting 24, maybe calculating out to 24.3, then it wouldn't really be an average in that case, where it would be a weight between the two.
Yeah, no. Actually, so I think I see your point. Your point is that why are you asking for averaging in 0.5 and you're not asking for averaging in 0.4? For anything, the thing is, if the number comes out to be 4.4, we take the fourth. If the number comes out 4.6, we take 5. When the number comes out 0.5, 4.5, there are two answers. With 4.5, actually there are three answers. Okay, if the number comes out 4, no problem. Number comes out 5, no problem. If it comes out here, we go to 5. This is 5. If it comes out here, we go to 4. Right?
Yeah.
Now, when you are here exactly halfway, there are three choices. You could go to 4, you could go to 5, or you could go halfway between the two. Right? And as I said, different authors have different opinion. All right? When I was writing the book, in the beginning, I had the opinion of being halfway. By the time I came here, I had a different opinion, which said that you take the lower one. So I'm just saying that I have to be consistent, at least in my own way. Similarly, you have to be consistent in your own way. So the thing is, one thing you will notice is that when you write a book, you have a lot of leeway. Because these things are not rules. You select your own rule, you justify your own rules, right? So and I have a valid question myself, whether, being halfway basically decreases the discontinuity. That's all there is. The thing is, if you were to plot percentiles here, so this is the some percentile, let's say this is 10 percentile, this is 11th percentile, this is 12th percentile, right? The numbers will go generally up, and there is a break whenever these things, rounding happens, so the value will go up like that. Right? And so I have to think about that part, is that basically, is one is better than the other. Yeah.
In general, since it's an art, can we just go with the best number that fits our data?
Okay, so I think let me answer that question like this. If you have a reason to go somewhere, then justify again, if you can justify that, because somebody else will question. So it's just like he is questioning why I'm taking half and not, halfway, and why I'm taking halfway and not taking the lower one, right? So people will question you, so you have to have a justification for that.
By the way, the rule of rounding also changed in the last few years.
Mm-hmm.
many new statisticians don't take 0.5 and just round up anymore
Uh-huh.
because you're biased up.
Yeah.
They don't want to be biased up, so they say that to be exactly halfway, you look at the number before that. If it's even, you round down.
If it is even.
If it is even, you round down. If it is odd, you round up.
Okay, all right. Okay, so here's fourth concept. Basically, what it is doing is with probability half, you go down, probability half, you go up, and the way you decide probability half is by looking at the lower number. Or you could flip a coin and do that too. I mean, you know. So every author is different and every belief is different, right? I mean, so the thing is, and you can justify that one too, is basically if you always do only one way or the other, if you always do lower, then you are biased. And that's a valid, very valid argument. If you always do upper, then you are always biased. If you do halfway, I think I am avoiding the bias. Right? So halfway is better in that sense, right? Our other way to avoid bias is to do this flipping. Yeah.
I have a question about the NQR.
One minute, let me write this down. This is a good point though. Okay.
I have a question about the NQR. The result, 0.65, I mean, what does it tell me? I don't understand the idea behind this.
Yeah, okay. So basically all of these measures of variation, higher is bad, lower is better. So all that is nothing. Basically, it does not really have a, so if I give you something has a SIQR of 0.65, is it good or bad? I don't know. But if I give you something else which has a SIQR of 0.7, then 6.65 is better. Okay? So this is basically a measure of variation. The lower variation is better. Right? More reliable, more believable, more, you know, so on and so forth, right? So all of these measures of variation, they are good if they are low. By the way, 10 percentile is not a measure of variation. Measure of variations are the ones that we talk about, you know, which is basically, this is just a one point in that variation thing, right? These percentiles. But if you take 2 percentile, then you get the range. That is the measure of variation. So if I just told you 10 percentile, you really don't know how high it goes. You just know that, you know, 10% of people are below this. But, you know, so you really need 2 points to get the variation. Yeah, go ahead.
So it's usually used to compare between two experiments or two systems?
Yeah, right. So what will happen is, the reason I am doing all this is because when we estimate anything, you know, so let's say we estimated that this processor is twice as fast as the other. Instead of saying that it is processed twice as fast as the other, we will say that it is somewhere between 1.9 to 2.1 times faster than the other. So we'll give two ranges, confidence interval, right? And so I'm getting you there to the, so that you can make a statement which is true as opposed to just saying 2 which may not be true. I mean, in the sense that it is hiding some information. Just like if somebody said that this river is 0.6 inch deep or 6 inches deep, and would you cross the river, right? So you say, well, this is not complete information. Tell me, you know, the what is the maximum depth there? You know, in that case, for example, maximum depth will be more important than anything else. I wouldn't care for 10 percentile or 20 percentile because I have 10% chance of, you know, dying. So I don't want to take that chance. Right? So I would say, tell me the maximum depth of this thing. I don't know swimming. So I just want to walk through a river, right? So you see, there is a reason for us to know the minimum and the maximum. All right. So here's a flow chart. When to use what? If the distribution is bounded, then range is good. If the distribution is not bounded, is it symmetrical and unimodal? Okay, first of all, what is unimodal? Remember the mode. What was the mode? Mode was the highest point on the graph. Right? Unimodal means single mode, means only one highest point on the graph. Right? Bimodal means there are two highest points on the graph. Anybody remembers the bimodal graph? And trimodal and so on and so forth. So if it is unimodal and symmetrical, so it looks like almost like a normal graph, bell-shaped curve, then you use coefficient of variation. And if it is not symmetrical, that is the problem most of the time. Things are not symmetrical. If they're not symmetrical, then you have to do some kind of percentile or SIQR. Then coefficient of variation does not give you the information that you really need. You see, suppose things are so biased so that most of the things are small and then few things are large. You get coefficient of variation, it looks like that everything is symmetrical around the mean, which is not the case. For example, exponential distribution, most of the things are small. Yeah.
But what does the coefficient of variation really gives you?
Oh, it gives you an idea that so thing is, when you see something and you see the coefficient of variation is small, like 2.2, 0.3, then you know that this is somewhat a stable number, as opposed to if somebody gave me something with coefficient of variation of 5, then I would be worried about it, that I think this is too much variance.
Yeah, so it's the standard deviation divided by the mean.
Yeah, it's the ratio. So no, that's basically the thing is generally the quantities that have in few decimal point, like 0.1 or 0.2 or 0.01, those are really good. I mean, those are really stable. As opposed to anything more than 1, people will start questioning. But as I said, there is no one number I will point out here because it depends upon the system. It depends upon the damage that it will do. And if it is your life and death question, then you better not have a standard deviation, a coefficient of variation of 0.1 even. You want to have a 0.001. Things like that. All right, so I think this is English version of the previous flowchart. Let's just go through it. The decision rules are not hard and fast, first of all, and there are systems in which all these rules are violated. So this is an example here. For example, network. You never design a network for average traffic. The average traffic on the network is 2%, right? So if you really wanted a Ethernet for your office, and actually if you go to a single office, then it is probably even lower. 2% is for a whole site maybe. But if you go to a single office, my utilization might be 0.1%. Okay? But when I need it, I need the network. I need that gigabit and not 0.1% of a gigabit. Right? So the networks are designed more on the upper range, worst case. All right. So the networks are highly skewed, and so we generally design for 90 to 99 percentile of the load levels. And so you would rather specify percentile. Similarly, anything that is basically, say for example, computing power. Most of the time your computer is idle. Right now, for example, you're sitting here in the class, your computer is idle. Okay? And in many cases it is on and consuming power as well. If my computers, for example, one that is in the office, actually none of them are, both of them are here, but if there was one in the office, then that would be consuming power. So it is important to know. But basically the idea is that we generally design it for when I need it, I need it. So we don't design it for average. Power supplies are designed for peak demand, because if power supply even went for a little bit above the capacity, it will burn up. So we don't want the fires to happen, so we don't design it for average load on the power supply. And then percentile found, so the one problem with the percentile is that you have to sort the data. So this is one of the earliest papers I wrote called P square back in 1984. So that is about 16 plus 12, 28 years ago. The problem that we ran into is that the data is continuously coming, and every time a new point came in and we need to calculate the median or quartile or 90 percentile or something, we have to sort the whole data set. You have million point, now million plus 1 point, you have to put that in the right place and then figure out which one it is. Now we don't have a space for million points to be stored, right? So we kind of we developed an algorithm where you don't store the whole data, you just store a few points, maybe 5 or 6 or something like that, and then you can still calculate the to very good accuracy, you can calculate any quantile you want. So that was published in a very prestigious journal actually. And so I think it was CSEM, I could be wrong, but anyway. So the idea is there are algorithms for what we call on-the-fly estimation of medians. You understand the problem? Problem is that if you're getting the data continuously, you don't want to store it, but you still want to be able to tell the median and the 90 percentile and 95 percentile. So there are such algorithms. All right. And then there is a summary box in the book. Okay, so much about, first we talked about the central tendencies, then we talked about dispersion, which is the variance kind of thing. Now we are going to totally different thing. We are going to go into the distribution. Before I go into distribution, any question about dispersion? None? Then we move on to distribution. And you remember the problem we ran into when we started talking about the issues that people can show any distribution, whether it is exponential or normal, by just proper selection of the bin size. When you plot a histogram, depending upon the bin size you choose, the distribution will look very different. So we want to avoid that problem. So one simplest way is that you do a histogram, which is done by putting the things into buckets. And if you take very small buckets or cells, as they call it, you will see a large variation. Some buckets will have 2, some buckets will have 200. Right? On the other hand, if you take large buckets, then you won't see that much variation, but you would lose the information. So you can really get into different conclusions. So one of the guidelines that people say is that if the cell has less than 5 observations, the cell size should be increased. So you really don't want to have some cells being empty, or some cells being 1 or 2 while the others have a lot more. So this is, if you are going to do a histogram, then this is one guideline they say. But we will avoid the histograms totally in this book or in this whole class. What we use is what we call Quantile-Quantile plots. Okay, so I have to explain to you what is Quantile-Quantile plot. Q plot. And so what you do is that, actually it's better to show you a graph example. Is that, let's say you wanted to, you had some data and you want to see if it is normal or not. So what you do is you go and find out what are the normal quantile. If something was normal 0, 1, its mean would be here, and then some observation will be below and some observation will be above. And so if you have 1, 2, 3, 4, 5, 6, 7, 8 observations, you just take 0.125, 0.25, and like every 1/8 you increase, and you read in the table what the value should be. Okay, 12.5 percentile, 25 percentile, 37.5 percentiles. That is your X value. And then you take your data and sort it out, and according to your data, what is the 12.5 percentile, what is the 25 percentile, and so on and so forth. You take that and you plot this. Okay, your data versus a normal quantile, standard normal quantile. If it is a straight line, then it is a normal distribution. All right. And now the question is this a straight line? Right. Now this is the beauty, is up to the beholder, right? Is that, yes, for me it is a straight line. For some people they say, no, this doesn't look like a straight line. So this is up to you. But at least you know how far from the straight line this is. All right. For most purposes, this is a good straight line, and this data has a good closeness to the normal distribution. Okay. Now, having given you the example, let me give you the theory back. So, the theory is that if if you take the ith quantile, all that means is that qi equal to fxi. So the value of x at which the cumulative distribution CDF becomes qi is what you are looking for. So let's say you are looking for 90 percentile, you will put 0.9 is equal to fx, and whatever x value you get, that is your 90 percentile. And so anyway, I think it's much easier to explain by this quantile plot than all that theory. But the idea is you can do this for other distributions as well. So it's not just normal. Suppose you want to see if something is exponentially distributed. Then you will take the exponential quantile on the x-axis and your quantiles on the y-axis and see if it is a straight line. All right. Now, since you'll be doing normal quantile quite often, you don't want to go to the book to look at the values. So there is a shortcut. The shortcut is that this formula gives you the normal quantiles very close to those in the book. They are very close. So this is an approximation formula. So you want the qith quantile, you just take qi raised to 0.14 minus 1 minus qi and so on and so forth. So if you want to program all this in Excel worksheet, one way is that you put that table in the Excel worksheet, whole table, which people can do, or you can just put this formula. So most of the time we just put this formula. This is much easier to just write this formula than to put that table in. Okay? And now let's just take the example. So the example is that the errors were found to be these values, minus 0.4 and blah, 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 up to here, right? So we want to see if this is normal. So what we do is, first of all, we sort this out. And after sorting, we get these values, minus 0.19, minus 0.14, and I'll leave up to plus 0.19. And we write down 1 through 8 number here. If this is I, then we write down I minus 0.5 divided by n. N is a 8. I is 1. So 1 minus 0.5 is 0.5 divided by 8 is 1/16.
Why 0.5?
Why divide half? Okay, I mean that is basically we are what we are doing is because there is something which we haven't measured. So something between 0 and 1. We don't know what the 0 value was. We know the first value, but we don't know what the 0th value is. Similarly, there is the 8th value, but we don't know what the 9th value is. So we just basically are taking that this value represents 0.5th quantile, and so this is I minus 0.5 divided by n. Similarly, then basically everything else continues because you just keep adding 1/8, 1/8, 1/8, 1/8, 1/8, and rather than saying this is 100%, we say this is 1/16 less than 100%. So we are leaving out 0.5 on the lower side and 0.5 on the higher side. So if there are 8 values, the question is, have you found the minimum and the maximum? And we say we haven't. So we leave some room for the minimum on the lower side and some room for the maximum on the upper side, and that is why 0.5 is there. Yeah.
Sorry, so the 0.5 is just arbitrary number, or it's just a number that you calculated according to the...
No, this is a fixed number actually.
Okay.
0.5 is always used regardless of n. So even if you had 100 observation, you would put I minus 0.5 divided by 100. N is 100. N is the number of observations.
But the 0.5 is
Fixed.
fixed. Okay.
Okay, let me explain one more time on the chart here. There is no eraser, so I'm just going to so your values are here. So we are calling this, what quantile is this? We don't know yet, right? But we could call it 1/8, or we are calling it 1/16, because basically this is, we could call it 0, for example. We could call it 0 or 1/8. 0 would be minimum and 1/8 would be, because there are 8 observations, right? We are calling it 1/16. So 0 would be here. This is 1/16. The 8th observation is 1 minus 116, and then this is 1 is maximum. We don't know 1 and we don't know 0. So we are just putting all our 8 observations exactly, in the center of the range. You're not able to read something?
Yeah, if you can write it bigger.
This is, I didn't write big enough. See where is space. So the thing is, this is 0, this is 116 and 1 8.
Okay.
So we are putting our first observation. There are 8 observations, right? So we could call that first observation either the minimum or 1 8. We are taking halfway. So going back again. So yes, 0.5 is a fixed number. We take I minus 0.5, divide by the number of observations, and we write down this value. This is the quantile we are looking for. Then we go into the table and find out that quantile. If you go to the table, you will find these values. Or you can calculate from that approximation formula, you will get these values. This is your x value, this is your y value, and you plot that, and if it looks like a straight line, then it is a straight line. Then it's a distribution that you are expecting it to be. All right. Now, interesting thing about QQ plot is that it not only gives you the distribution, it also gives you more information. For example, this one says that this is very close to normal. This one says it is close to normal except in the ends. Right? Now, these graphs are different. This one becomes horizontal, this one becomes vertical, this one becomes vertical and horizontal. That gives you some more information that we will discuss later on, not in this chapter, but later on. That this tells you what to do with the model to make it like that. Okay? So it not only tells you what is wrong, but it also tells you where it is wrong and how to fix it. Okay, you can fix your model so that this thing will become normal. All right, I think I will, let me finish this then. So the summary is that the sum of a large number of random variables is normally distributed. That is the central limit theorem. And then for central tendencies, we can use mean, median, mode, arithmetic mean, geometric mean, harmonic means. And for dispersion, we can use range, variance, percentiles, quartiles, etc., and we had a flow chart for both of them. And then finally, we talked about QQ plots, how to draw the distribution, right? So that brings us to the homework. And the homework is to plot a QQ plot. All the values are given, you sort them out, and are these errors normally distributed? And the data is available, so you don't have to enter the data. What I will do is I will put it on the website. You just go and download the file, and then you can just put that into an Excel worksheet or whatever you are using. You will probably be using Excel worksheet to do all this calculation anyway. Okay? So what you need to do is prepare a table like this using an Excel worksheet. This column will be given to you that you can download. Okay?